Hello and welcome to another episode of the Oxford Online Maths Club. Today we're going to do some maths. I hope that's okay. Thank you for joining us, especially if it's your first time. Welcome to the Maths Club. We've got a live chat running. It's not on YouTube, it is on Vvox. There is a link down there and also in the video description. If you're watching live, you can join the live chat. I think today I've got a student moderating it, but I don't want to put them in the spot in case they haven't yet worked out how to use Vvox. Vvox is new and excited. We've got a new person. Their name is Izzy. Hi Izzy. Nice to have you here. One person in chat hasn't put their name, but they say they got an offer for Pembroke, so congratulations. Oxford letters are going out at the moment. And somebody else has put, I realise now, happy emojis, but also they said they got rejected. So sorry to hear that. Raphael is in chat. Hi Raphael, who also says they've got an offer. Very excited. Hopefully those two people might even turn up. I saw a tweet on Twitter at the start of the year which said I just started talking to a random person in a maths lecture and we found out we both watched the Oxford Online Maths. Anyway, never mind. I'm not saying that you have to meet each other, just that would be all right. Also, if you aren't going to Oxford but you end up at the same university as someone else in chat, then I still expect you to say hi. Somebody's going to New College, which means that I might be teaching them. And Jack's here too. Hi Jack. Emojis always indicate irony. Right, okay. Liam has fixed some code. Good job, Liam. Assuming Liam is the person who sent me some, I'm inferring from that Liam is the person who sent me some Pascal's triangle code. If you watched last week's episode, either live or on the replay, it's somewhere on this YouTube channel. There was an episode out last week where we looked at Pascal's triangle, and I do want to talk about that a little bit again because some of you sent me stuff, which doesn't always happen, but you sent me stuff, so I want to talk about it. Marcus is here. Matthew is new. Hi, welcome everyone. Great to see people here as well. You're also, it seems like, working out the system that Vvox is anonymous by default. You don't have to put your name on things. If you want to, you can put a name on things. There's no police, right? Like, you don't have to use your real name. You can, if you've always wanted to try out a different name, then here's a chance to try one of those as well. People are getting offers, and also people are not getting offers, and I kind of want everyone to be happy either way round. Let me check. How is everyone's day today? While I do the coming up, I found out how to do this in Vvox. This is a thing we used to do on a different show. I would like to know, how is your day today? Is that working? That's not working. Can I? Well, I mean, people are voting. You just can't see. Can I show results live? There we go. Oh, look. To 4 significant figures. Thanks, Vvox. Right. Okay. This is a vote for how was your day. I'm always interested in how your day was. Hopefully we're going to do some maths and see what effect that has on your day. 46.15% have voted 5 stars. What a nerdy thing to do. Coming up today, we have got more triangles because I want to revisit some triangles in light of some triangle stuff that people sent in. And I would like to show you some facts with circles, including one problem that's sort of new to me. I didn't know about it. Maybe you don't know about it either, so it's kind of a new problem to both of us, I hope. But it is actually a very old problem that people have been interested in for a while. So I would like to get onto the circles problem as well. If we're getting close to the end, and I haven't said anything about circles, maybe remind me to talk about circles at some point. If you haven't joined before, it's quite rambly. There's a lot of talking. Hopefully, I'm going to encourage people to actually do some maths as well. That vote has, it seems, stopped. The average, in tiny writing there, the average is 4.19, which I think is the highest I've ever seen for a vote on how's your day going. As always, I'm looking out for people who vote for kind of 1 and 2 stars. If you're not having a great day, then hey, you've tuned in to see some circles. I don't know if that's good news or bad news. Brill, right, okay, let's get that off the screen. Let's stop this. Let's see if I can go back to the Q&A so that we can have some, how do I, oh no. Yes, there we go. People are here. You too. If Cat was here, but what's the last one? Brilliant, okay. And I now have, I think, a student moderating chat because chat has kept moving while I was doing poll stuff. It's a complicated show. It's a complicated show. And people have been here for a couple of years, oh my goodness. We got a couple more people telling me they've got offers in as well. Marcus, I'm having a, I think, 5-star day because the office is a mess. Please don't look at my background. The office is a mess. We've been doing a lot of events this week. Before term starts, we get to use the building to do fun maths events for sometimes for local children and sometimes for people from around the country as well. We've been doing a thing called It All Adds Up. Kai says hello to the student moderator. To check if I've got a student moderator, I'm going to leave that there until, so Kai will know. Kai is the canary. Right, and Charles is here too. Hi Charles. I'm in year 12, but age 17 to 18 years, that's fine I think. I don't know, I think that's fine. I think there are older people than that in year 12. Right, okay, Pascal's triangle, really quickly, because I have some other stuff that's new. I talk too much. Last week we talked about Pascal's triangle. We looked at a pattern with odd and even numbers in Pascal's triangle. The pattern went a little bit like this. Pascal's triangle starts by having some ones at the top, those are odd numbers, and then the next row down has got some odd numbers in. The next row after that is all odd, and then after the odd numbers there's this rather pleasing pattern, he says, trying to work out Pascal's triangle, where you get these even numbers, because odd plus odd is even, and then after that, the even numbers, 4 plus 6 is 10, welcome to the Oxford show, you get these kind of triangles forming, where it forms this kind of triangle. These are going to go inwards because even plus even is even, so we end up with a 20 down here, but running down the side, on the edge of this triangle, we get things like, oh my goodness, I really can't add today, chat. We get things like 15 and 6 and 1. So it's a kind of nice pattern that you get these kind of small triangles and you get these larger triangles. I guess technically I should draw that way up. You get these larger triangles, you get this lovely pattern forming. And something I said was, it would be nice to try this out for sort of multiples of 3, for multiples of 4, maybe for multiples of 5, or powers of 17, or whatever else you want to do. And I think what was really nice is that some people went and actually tried that, and then sent me either their code that they'd used to do it, or sent me the output of their code. So let's try and imagine what you guess might happen. If you haven't tried this, which is most people, including me, I haven't tried this. So it's a surprise for me when my inbox, oh my goodness, surprise for me when my inbox started filling up with people sending me Pascal's triangle, because it's always nice to know that people are actually out there watching. Sorry, I was also trying to add small numbers together while talking. Do I discriminate against schools that stopped at A-levels age 17 and finished A-levels age 19? That sounds fine, that sounds kind of normal. Oh, I see, that's like out by one. That sounds normal. A-levels are A-levels. Casey says it seems like a fractal, and I'm afraid I'm not doing Maths Fest in London. I know Maths Fest exists. If you're going to Maths Fest, I think you're going to have a great time. I'm not going to Maths Fest. Maybe I'll have a great time anyway. Oh, now that sounds bitter now. Can I redo that? No, it's live. It's live. Anything could happen. So I want to thank Kai. Thanks, Kai. Kai sent in some pictures where, as well as generating Pascal's triangle and checking whether things were odd or even, Kai went kind of the extra mile and also managed to get it to display nicely. If you've done stuff with computer code, getting it to display equilateral triangles is surprisingly tricky. Anyway, Kai made these, which I think are really nice. So we're going to stare at these quite just for a bit. These are the patterns with red for the ones that are multiples. Looking at the left there for multiples of 3, that's the pattern. Which ones are multiples of 3? Maybe we can talk about what you can see in that picture. In the middle it's multiples of 4, which I think is even crazier. And then on the right, for multiples of 5, there's something great about humans in the way that by the time I see the 5 one, my brain is already thinking, oh yeah, kind of looks, they're all crazy, but kind of by the time you see the third one, you think, oh right, kind of looks kind of about the same. Someone says, is there a point in reapplying? If you reapply, it's treated as a separate application. It doesn't get linked back to your previous Oxford application. If you've got offers to do maths somewhere else in the UK, there are loads of great places to do maths in the UK, and I think I'd encourage you to look into just starting a maths course rather than taking a year out. Okay, can someone tell me? So Kai's made these pictures, and I think they're great. But what can you see in these pictures for where the multiples are? This is a kind of discussion topic. I don't think we do enough of these in maths class, right? The maths class? I don't think we do enough of these in maths lessons where you have some pictures and you discuss what you can see. Well, people are being a bit shy, even though it's anonymous. Kai is here in chat. Hi, Kai. Kai says, it's a bit embarrassing. I think you're fine. I think it's good. Casey has put something like, I'm going to take a few opinions. I love this. There are a lot of triangles. Thank you. I agree. There are a lot of triangles. It kind of inherently wants to make triangles in some sense. Once you've got a few multiples, the things underneath tend to be multiples as well because they're adding together multiples. If you add together multiples of 4, you get a multiple of 4. So it tends to make triangles. I love that because I'm not sure people would say there are lots of triangles if we did this out loud, because it doesn't feel like a very clever thing to say, but it is really clever. It is a genuine observation. There are triangles in these pictures, like the upside down red triangles. Did I say triangle, or did somebody else say triangle? This is how to get really paranoid. Start a live stream. Start a live stream and you'll just become really paranoid really quickly. The Triforce is a good suggestion. I can see Triforce-like pictures. So Triforce is the picture that's like this. It's in the Legend of Zelda games. And I'm allowed to say it without getting demonetized because it's not actually copyrighted, and also because this live stream is not monetized. They're stacked in, equal edge triangles of n-1. Something about n-1. So the one that stands out for me, can I point? Marcus has backed up Kai's calculations. If I can point, the one that stands out for me is this bit here. This bit makes me go, ooh, because that's sort of really clearly as something with 4 upside down triangles across each side, and 4 is 1 less than 5. It just feels like the sort of thing that's going on. If I now look over here, I can sort of see that up here there's kind of 2. Over here there's kind of 4. So there's something like n-1 going on, maybe? I don't know. Maybe I'm just I don't really know what I'm labelling. Maybe there's something going on here. And then 4 looks like a bit more complicated. It doesn't really fit in. Yeah, so suggestion in chat. Somebody else, thank you. Somebody else in chat has admitted to saying triangle. It wasn't me. They're next to each other on a keyboard. Typing it, not a big mistake because the letters are next to each other. Saying it would have been a really bad mistake. So would it be more enlightening, this is a question, if instead of just showing red and white, for multiples, use a different colour for each possible value modulo n. Modulo n there is a short way of saying for each possible remainder. It's something some people would learn at some point. Different colour for each remainder. I've tried this, it's really pretty, and I'm not going to show you. I've got them on my computer somewhere, the outputs with different colours in. Really great. Annoyingly, I'm just going to recommend that you try that yourself. If you can teach a computer to add numbers together, which if you know how to make a computer do some sums. If you look at the bottom of the multiples of 5, it looks like we're about to get 2 massive triangles. This is good, actually. I agree. You have to look really closely. I'm kind of surprised that you can see this, but there's like a single white 0 in the middle of this bottom row, and 2 massive rows of red, which I think are going to produce these 2 massive triangles. Oh, you can't actually see it because it's behind chat. Let's zoom. I think they're going to produce 2 massive triangles, and that's quite exciting because I reckon there's this question of how often is it going to do that, right? How many massive triangles is it going to make before it does something else? What do you think it's going to do inside these regions? And I've got some ideas, but they're still theories. There's something nice about being a mathematician where you have a question, you maybe give it to a computer, and the computer spits out an answer maybe, or you check some numbers and you get an answer, and then you kind of immediately have more questions. So after these 2 big triangles, what do you think happens? What's your guess? What's your intuition for what happens after those massive triangles? Triangles pointing the same way. Yeah, I expect triangles pointing the same way. In a bit like, I guess I expect a repeat of this sort of bit on the left. You can't really see where I'm pointing. I guess I expect this thing to happen again over here, because the kind of starting conditions are about the same. It's over on the left of the triangle, if that matters. There's a big red triangle on the right, and on the left it's just got these kind of 2 white spots at the top. It's got a 1 at the top, and then some multiples of 5. And so I feel like maybe it'll do exactly the same thing again. So maybe we'll get a repeat of the 4 triangle part. I agree with that. Maybe, but that's just a guess, right? Just a hypothesis. One of the things about being a mathematician is getting better at guessing. I know you at school, if you're GCSE or A level or equivalent, then you never have to do any guessing. Like you always have a method. You always know what's going on. Guessing is surprisingly is a good way to make progress. Right. Okay. I'm not sure I do have a student moderator, or if I do, the student moderator was in for a little bit, moderated some chat, and then maybe got disconnected, which would be a bit sad. But hey. Okay. Oh, more observations. So we've looked a lot at the picture of multiples of 5 over on the right here, but in other places, at the bottom of multiples of 4, there should be 4 equal sized triangles and one larger one to complete the upside down triforce. So there's a theory that this upside down triforce, 1, 2, 3, there's some sort of upside down triforce going on here, and then maybe that's repeated, and then after that I'm not really sure what to expect, but it feels like maybe, yeah, there's some bigger structure going on in here. A clue to what I think might be important, but nobody said yet, is 3 and 5 have something in common. They have a lot of things in common. 4 is a little bit different, which is why I think it's why the pattern is a little bit different. I'm trying to be a little bit cryptic, which is probably annoying, sorry. Yes, it looks like the 5 one could be a fractal by putting the big triforce in the small one at the top of the other parts. Yeah, I think it is a fractal. I think it is. I think it's going to do, I think the big picture with all the question marks down here, I think it's this again, this pattern. I expect 4 of the big ones before it does something huge. Cool, good. Okay, what's on your whiteboard, someone said? Plans? It used to be the plan for we should do an online live stream sort of thing for maths, and then that's happening now, so now it's plans for something else. Someone's put Prime in the chat, which, you know, and then Prime is getting loads of play on TikTok at the moment. That all the teenagers are going mad for Prime, and I think that's really good. It's nice to see, you know, number theory getting the prominence it deserves these days. So yeah, I don't know, like hashtag Prime seems to be doing extremely well. So I thought maybe I'll give some Prime content and you could all get on that bandwagon. Right, good. Oh, there's some really good theories. Oh my goodness, here we go. Oh man, I thought you were saying trifle this whole time. It's the accent. I don't even know what the accent is. Looks like cellular automation. Can't say that. Yep. Looks like one of those cellular things we saw last week. I want to do some other shout outs. Yeah, we did talk about cellular automations a little bit last week. I think I want to do a couple more shout outs on that theme. So I also want to shout out very quickly to Holy Pumpkin. Holy Pumpkin sent in some Python code. This is a weird string of words. Holy Pumpkin sent in some Python code that predicts when it's all odd calculator. And we did some sort of pattern spotting, and we were looking at when does it happen that all of the rows in Pascal's triangle are odd, like how in this row here at the bottom, 1, 7, 21. Whoa, those are all odd numbers. I don't think anybody's really proved that for me. I mean, in this maths club. Out there, if you go and Google it, I'm sure someone else has proved it, of when does that happen, and here's why. But you might like to have a think about that, or think about when are all of the numbers in a row of Pascal's triangle odd. It happens here, 1, 3, 3, 1, and it happens down here, 1, 7, 21, 35, 35, 21, 7, 1. When else does it happen? I guess up at the top. And then somewhat later on as well. I think like mathematicians, 4 is similar to 2, as every multiple of 4 is a multiple of 2. That is a great. That's lovely. I like that. Yeah, the coloured in bits for the multiple of 4 have to be a subset of the, if you did a version with 2, because if you're a multiple of 4, you have to be a multiple of 2. Right, good. Okay, so it's sort of a subset of a different one. People are catching up with some hilarious banter. There's a little bit of chat lag, I think, unless people are laughing at something else. No, I was hilarious, but a good couple of minutes ago. Good, right, okay. So shout out to Holy Pumpkin. I don't know if you're here as well, but you sent me some Python that correctly worked out with computer code when that would happen up to about 10,000 or something. And we also mentioned cellular automata, so I just want to shout out Martina as well. I didn't ask if I could do this, sorry. Martina sent me, I had a throwaway comment to say that you could go and do the electronics. You could make, we had these kind of OR gates, and I don't really know about OR gates or computers or something, but I said as a throwaway comment, you could go and plug some of these together using electronics, and Martina went and actually did it and wired up an Arduino to a breadboard and had some lights and on OR gates and demonstrating the code, and it was really exciting. I owe you an email, Martina, sorry. By the time you're watching this, if you're not here now, by the time you watch this, I hope you get to get an email back. I'm really bad at sending emails back. Prime's an energy drink. I'm not on that bandwagon after all. Well, I'm still going to talk about prime numbers anyway, sorry. Ooh, all the numbers in a row. Hang on. Oh, look at this. Hypothesis in chat. Let's read it. I've just noticed that the numbers in a row excluding 1 are always multiples of the second number. Is that true? Oh, there's something going on, isn't there? I kind of know what you mean, right? So you're saying second number, 7. Hey, look, these are all multiples of 7. Correct. And also it works for 5. Hey, look, these are all multiples of 5. Correct. Also works for 3. In a silly way, these are both multiples of 3. Actually doesn't work for 4, because 6 is not a multiple of 4, and it doesn't work for 6 because 15 is not a multiple of 6. But maybe it just works for odd numbers, or sometimes it works, sometimes it doesn't. And no, Kai, prime is an energy drink, so that can't be right. Good. Okay. Is it when it's odd or when it's prime? The best way to work out is probably to generate. Calculate down to the 9th row, because 9 is odd and not prime. So maybe that's good. Gosh, I can only be bothered to do this corner of it. Conclusive 36 is a multiple of 9. What if I go over here? 50, no. This is real bad times for adding. 56 maybe? Not feeling that confident. 84? Can't add. Right, homework. 9 doesn't work, so maybe it's primes. Okay, right. Hypothesis generation is really good. Where hypothesis generation is where you try and spot a pattern. If your pattern doesn't work, you get to change your hypothesis a little bit, regenerate a new hypothesis. Brilliant. Okay, so I was really excited that people sent in stuff. Shout outs again to Kai, Holy Pumpkin, and Martina, who showcased some stuff that's going on. Oh, Prisma is here. Hi, Prisma. We got some chat moderation going. Nice, good. Okay, Prisma's current student doing maths and philosophy. Phil is short for philosophy. N is short for and. Maths is short for mathematics. Year is short for year. I'm not going to do every word. Right, okay, triangles. How are we doing for time? Not great. I'm going really slowly. It's Prisma's back. People are happy to see Prisma. Good. Prisma, if you scroll down, some people are posting that they got offers. It was lovely. Some people are posting that they didn't get offers, but they seem maybe happy anyway. We'll find out. Okay, so triangle square problem. This is just another problem with a triangle in it that I did recently for fun, and I thought maybe it would be fun to do it again. You can let me know that it's fun or not fun. Works like this. I've got an equilateral triangle, the pink equilateral triangle here, all the sides are the same length. And I put it in a box because I want to send it in the post. I need the triangle. Triangle fits. The trifle fits in the box. Good. But this is not the smallest square box that I can put the triangle in. For postal reasons, I would like a smaller box. The way I can do that is to rotate the triangle a bit. Let's get rid of those markings. Okay, so I can rotate the triangle a bit, and if I do that, then that frees up some space. You see now, look, it's not quite touching on that side, so I can make the square box a little bit smaller. Okay, that's pretty good. I can go further, but I don't want to go too far, because if I rotate all the way around like this, then I'm back to the original picture. I'll go vertical on that side. I'm back to the original picture, and that'll be the big box again. Look, I've got to make it bigger to get that corner in. So somewhere in between, there's a kind of happy middle where the triangle fits inside the smallest possible box. And I think it's a fairly natural question. How big's the box in that small? How big's the smallest possible box? So I want to make the smallest possible box. Let us say, let's say side length 1 for the triangle. Otherwise you would say something like, oh, we'll make the triangle really small. It's an equilateral triangle. This is no longer a sentence. Maybe it was never a sentence. Okay, suggestions in chat. Somebody with an offer wants Prisma to say whether they should accept their offer. Prisma? Love for the shade of pink. We've been using the shade of pink for 4 years, and this is the first 3 years. This is the first time someone's appreciated the pink. It's in all the thumbnails and stuff. I love it. It's brilliant. Chat wants to go 15 degrees. Why 15? I can't remember the last time 15 was the right answer for a... Not that you're wrong, just a bit of a random angle, right? But 2 of you, look, 2 of you. So it's kind of random, right? Oh, would the area of such a box be twice the area? The triangle. That is a great question. Has that appeared on chat yet? Can we get that in? There it is. Would the area of such a box? I don't know, let's find out. In some sense, maybe. I sort of know what you mean. Maybe explain why? Halfway to vertical, because 15 degrees is halfway round. It's pretty good. It's pretty good, I quite like that. So I think I used the phrase happy middle earlier, or sort of happy medium. So maybe going 15 degrees. Let's label that. Maybe that's the best, because it's sort of in the middle. And I would like to point out now that there are 2 challenges. The first one is a kind of geometry problem. To say, hey, if the side length of the equilateral triangle is 1, and that's 15 degrees, then how big is the box? And that is not super easy. I've seen easier questions before. This is not the easiest question I've ever seen. Because, hey, how big is cos 15? How big is sine 15? Tricky. Can I repeat the question? Repeat questions. Okay, so I've got a triangle of, an equilateral triangle of side length 1. I would like to fit it inside a square box. What's the smallest possible square box that it fits in? It's really easy to put the triangle inside a box of side length 1. It definitely fits because, I don't know if people have calculated this, but before, but equilateral triangles are not as tall as they are wide if you sit them flat on the ground, because the sides are at angles. Sorry, that came out really stupid. So equilateral triangle would fit in a box of side length 1, but you can probably get it in a slightly smaller box if you're clever, if you shake it around a little bit. That was the question. No, 15. People are agreeing 15 degrees. Okay, so two questions then. One, if 15 degrees, what's the side length of the box? And 2, why 15 degrees? And I think the second question is much harder than the first one, even though the first one is hard. Whoa! Prisma has posted a wall of text. Thank you, Prisma. Things that appear in pink on chat are either me or student moderators. Today's student moderator is Prisma. Lagging a lot. Is that me, or is that everyone, or is that just one person? Oh, hi, Jack. I'm just catching up with chat. Oh yeah, that is. Thank you, whoever posted this. Fit an equilateral triangle of side length 1 into a square box as small as possible. That is a much more concise way of stating the problem. I am not a concise person. Who is Prisma? Prisma is a current student. They're in second year. They're studying maths and philosophy. Good. Okay. I think maybe sine 15. People are doing some algebra, some arithmetic stuff in chat. think you can do this. So what would this be? Trigonometry then. If this is a right angled triangle, this is the hypotenuse, this is adjacent. So do I want cos 15? Maybe sine 15 gets a vote in chat. Oh no. Adjacent, I think it's adjacent, right? Can we get a vote? Yeah, maybe cos 15. I think cos. Cos 15, but then there's this kind of separate question of how big is cos 15? Does anybody know how big cos 15 is? Be a little bit surprising. I'm trying to keep the triangle the same but shrink the box, Marcus. So keep the triangle the same but shrink the box. Because the triangle is, I'm trying to send it in the post, but I would like to choose a nice small box. Maybe I'm Amazon or something and I'm trying to ship triangles to people. Maybe it's a sort of triangle subscription service. Oh my goodness. Wow, square root of square, what? 1 square root of 3 plus, don't know where that's come from. You could approximate cosine 15 with this Maclaurin series? People are telling me cosine 15 in chat. Is it? Cos and hypotenuse. Yeah, okay, we've agreed on cos 15. There's this sort of question about how big is cos 15. I have a couple of methods for this. One of them, and this is a little bit weird. I'm not sure if you're going to like this, but we do this. Yeah, okay, we'll do some double angle. This is a little bit weird because double angle formula is not one of the things that you learn in the first half of year 12 or equivalent, so I'm not sure if people have seen it, but bear with me. There's this amazing fact, you'll love it when you learn it, that cos 2 theta is equal to 2 cos squared theta minus 1. I love this fact. I think it's really good. It's got secret links to complex numbers. It's just lovely. In particular, this lets you work out, if you know what 2 theta is, then you can work out, so this is what the right hand side means, all squared minus 1. So here, I've put in 15 because I would like to know cosine of 15, and I do know cosine of 30, in theory. Is it root 3 over 2? Yes. So this thing, which I'm going to call it x or something, and then rearrange this and add 1 and divide by 2 and take a square root or something. Oh, is that the thing that someone put in chat? Oh, someone put in chat. Or use, angle formulae as well. Cos of 45 minus 30, that's a good idea as well. I like that a lot. If you know how to expand cosine of A minus B, if you've got a formula booklet, oh no, A-levels don't have formula booklets anymore. If you've found somebody's old formula booklet in your A-level maths classroom, then you can look up a formula for cosine of A minus B. If you like this sort of fact, then you will really like this sort of fact. This is even better. Advice for joining Oxford University, do as much maths as you can now. Have fun with it though, try and find fun maths. Do lots of maths and have a look at our website for how to apply, if you want to apply. Year 10s have not seen this fact. If you want a story, one of the first things that I learned when I started going to an after-school maths club is that fact on the board. One of the older kids at after-school maths club showed me this, and they didn't tell me why it was true, and they didn't tell me like what you do with it, but I could tell that it was different from stuff that I'd done at GCSE, and that was sort of one of the first things I learnt at maths club. And now, hey, look, we're doing a maths club. Oh, somebody else got an offer on Tuesday. Hooray! Brilliant. Maybe I'm still around in October. We will see. I'm employed year by year, so we will see. Depends if I do a good job this year, whether I get to teach incoming new people at new college. Not part of the course yet this year, in year 10. Is that year 10 in the UK? No. Year 10 in India? Was that India year 10? Okay. Oh, right, okay, height of triangles. Height of the isosceles triangle. Yes, okay, yes, brilliant, okay. It's an alternative method. I love it. It's an alternative method. It's sort of a proof of some of these facts. I'm going to read it out. This is anonymous, so I can't say well done and thank you to the person who put this, but this text here. Find the height of the triangle and the height of the isosceles right angle triangle with base being a side of the equilateral triangle. Yep, the isosceles right angle triangle with base being side of base. And then this length of the diagonal of this square and find the side length of Pythagoras. I thought I knew which ones we were looking at. There's a year 7 in chat. Hello, year 7 in chat. Links. Yeah, there are links to the Dimoivra. This is just a really good fact. It was a very good thing, first thing to find out on Maths Club. I put it in the second episode of this season of Maths Club, episode 54 or something. There's an alternative method. Oh, hey, right. Oh, right, okay, so you've got formula booklets. Okay. Some people in England, I think, don't have formula booklets, but I'm not sure. Okay, right. Alternative method for working out cosine of 15. Not sure I'm going to like this. So this triangle up here, we know quite a lot of facts about this triangle. Sort of 1 over root 2, right? Because it's a 45-degree triangle, I think. If you chase some angles around, there's like a 75 over here. There is a 60 degrees inside an equilateral triangle. That makes 135. So this angle is 45. I know this triangle. It's isosceles. So there's 1 over root 2. And then you can do something like call the side length of the triangle call the side length of the square x. So this is x minus 1 over root 2, and then do Pythagoras on this small triangle to solve for what x is. Ugh, nasty. Which is a bit of a mess. Okay. If you do that, then you have to write down some sort of Pythagoras equation. I'm going to leave it as homework, I think. Ooh, engineering at New College. What were they? Your math lectures, I think, are taught by the engineering department for the engineering degree. Sorry. You are welcome to come and hang out in the maths department if you like. We have a cafe. Our cafe is very nice. It's now becoming an offer holders kind of event. Good times. Alternative methods: use a calculator. For instance, also, yeah, you will. Yeah, sorry, you didn't have to learn that from an Oxford live stream. Oh, that's nice. Square root of 6 plus square root of 2 over 2. I think that is what I've seen before for the side length. Brilliant. Okay, which I think is what somebody told us earlier. So earlier, this method over here. Let's finish off my algebra. Give some like square root of a square root thing. So then there's a hard-ish question to do with surds, which is to say, oh, are these things actually equal to each other? So I quite like this question because it dances around with geometry, with algebra, with trigonometry, with surds. There's a lot going on. A lot of stuff going on in different places. I would like to work out if the area of the square, or square area for short, is twice the area of the triangle. I sort of think it might be. Or maybe not. Oh, I'm not sure what I believe. Because I can sort of see the rule that it's like base, height, divided by 2. It's a very convincing thing to say. Right? Okay, the base and perpendicular height are not one of the sides of the triangle, but does it still work? I can't remember if this works. I sort of think it might be true. I can't work out the square area fast enough. What's that squared? I'm having trouble, but maybe somebody kind in chat will help me out. The only year 7, maybe. Yeah, it's got a plus 0.5 that I don't understand. So I think maybe this is not how you work out the area of a triangle. Hey kids, remember when you're working out the area of a triangle, you want the base times the height, and they should be perpendicular, and one of them should maybe actually be the base of the triangle. Yeah, it turns out the square area is slightly bigger than I wanted it to be. This is annoying. I thought there was a good chance that the square area was twice the area of the triangle. Right. We can find the area of the triangle with Heron's formula. That is quite a bold thing to say. So timeout on that fact, because someone's name dropped heron in chat, and that is a name drop, not a bird drop. The name drop for heron's formula is that there's this amazing way to work out the area of a triangle if you only know the side lengths. It's not the best way to find the area of an equilateral triangle. The rule is that first you work out the semi-perimeter, which is the perimeter divided by 2. And then you work out the astonishing, I think it's 1/4 at the front, I think it's 1/4 of S minus A, S minus B, S minus C, all square rooted, is the area of the triangle. Heron's formula, amazing. Good chat. Good work, chat. It's a very strange formula. It's very odd. It's got all these semi-perimeters in. It's got to define a new term before it starts writing down a horrible square root. Pretty sure it's a factor of 4 out the front. You see, a very, very good calculator would be able to just 3/2, but then you've got to plug in the... So here the semi-perimeter would be 3/2, and then plug it all in. You get 3/2, 1/2, 1/2, 1/2. Not convinced about my factor of 4. Cool, right, good. Yeah, base times height divided by 2. Yeah, it's sort of cosine rule sort of thing. There's no quarter in Heron's formula. Okay, I'll get rid of my quarter. Thank you. Let's quickly... I'm sure someone else has done this already. Huh. I wonder why I thought there was a 4 in there. Oh! I have worked out where I got my factor of 4 from. It's from all the factors of 2 in my semi-perimeter. There's a different version where you use the perimeter instead of that. Let's not go there. Yeah. But these are better ways. In chat, these are better ways of working out the area of an equilateral triangle. Anyway, I feel like we've now got quite a good answer for question 1. If it's 15 degrees, what's the side length of the box? I'm not super convinced about the why 15 degrees. And I agree, by the way, that if that's 15 degrees, then this is also 15 degrees. I agree, that's true. And that does make it the middle of the rotation. The midline of the triangle is now 45 degrees above the base. So there's the middle. So halfway through the rotation motion. Not totally convincing to me that that's... Yeah, that's the best. You could do some theta. Oh yeah, you could do some minimize. Yeah, okay. You could set up the problem with angles in and try and solve stuff. It's a bit of a mess. There's maybe an argument to say something like, we haven't talked about this triangle at all. By the thing you've assumed it's 15 degrees, or you've claimed for question 1, you've said it's 15 degrees, so it's kind of the same. I think there's maybe something clever to say that if this triangle is not the same as that one down below, then you can tweak the triangle a little bit and fit it in a smaller box. I wonder if there's a method like that to say, suppose these triangles are not the same, the angles don't match, then it's not the best box. You can tweak it a little bit. Kai sent me some more, yes. Kai sent me some more Pascal's triangle stuff. If other people would like to send me things about Pascal's triangle, or things about triangles fitting in boxes, then you are welcome to do that. There is an email address on screen and in the comments, Maths Club. Oh, hey Zoe. You're mildly on camera, but only briefly. Zoe also laughed at the square ear joke, so that's pretty good. Yeah, if you rotate it any further, says Charles, and I like arguments like this, it would push the box in one direction. I think that is true. It sort of loses contact with one of the sides. This is the only picture where it's touching all 3 sides, touching both of those sides. Okay. Yeah, if you'd like to send me triangle facts, it looks a bit like origami. What happens if you cut it out and fold it? Right, good. Yeah, if you rotate any further. Oh, right. Was that Charles again? Oh, sorry, right. Symmetry in the diagonal square shouldn't favour one side more than the other. Yeah, I know what you mean. It's sort of like it should obey symmetry or something. That's quite hand-wavy. Okay, triangles in boxes. 15 minutes, haven't mentioned circles. Now try to fit a square in a triangle, lol. That is a good question. Writing questions is hard. That one's good. Okay. I would like to show you the circle problem, I suppose quite quickly, because it's 6:45. We're going to be done at 6. Put the structure on the Cartesian plane and go for it. I don't know about easy, but you can do some stuff. Here's the circle problem. You might have seen this before. It is vaguely familiar, maybe. Works like this. You have a fixed blue circle. This is fixed. And you would like to cover it with pink circles. Here are my collection of 5 matching pink circles. And I'd like to completely cover the blue circle using my pink circle. So if I do this, I've got a little bit missing, a little bit not covered over there, so I want to do something like that maybe. How big do the circles need to be? So at the moment, I think these circles might be, we might be in trouble here. These circles don't really feel big enough to cover all of this blue circle. How big is circles? And how should I arrange them? What should I do? The new old circles problem. So I'm going to give chat a chance to give me some suggestions, and I'm going to move the circles around in what I hope is a frustrating manner, so that people are frustrated enough to tell me how to solve this problem. Have you ever seen those adverts for mobile games where the game looks really easy, but the person in the advert is incredibly bad at it? They're like a CGI hand or something. They're just terrible at solving the puzzle, and that's on purpose so that you see the advert and you think, I can do better than that. So what I'm doing here is I've got a maths problem and I'm solving it really badly to try and get you to, circles intersect each other at the circumference of the blue circle. That's a really good idea. Let's just look at 2 as an example. If my circles intersect like this, then I'm kind of wasting some. I can move it in a bit and be fine. Move it in until it's like that. That's sort of be fine. Just get more of it covering blue circle for free. Maybe it's something to do with diameters. Yeah, they're terrible adverts. I'm sorry. One in the middle, and then try to cover the other with like a flower. Okay, I can do that. So this turns out to be quite hard to do because if I actually get the outside 4 like a flower, I kind of know what you mean, right? Flower like this, right? I wish I was recording when I found out that my whiteboard could do opacity, translucent stuff, because it's so beautiful. Do a flower like this, right? I guess for the flower I need to know how far apart should they be, but maybe they should be like just touching or something. That looks nice. If I do that, then there's kind of no middle bit, so maybe you want me to leave a middle bit. How big should the middle bit be before you... There's sort of some tricky stuff going on. Right, other things are going. Bunny says those trash ads, so annoying. I think string theory is solve time, no. Intercept in each other at the centre. 2 circles opposite, and arrange the other 4 in a similar way. There's this idea, maybe you have 2. I think I need to make the circles bigger. It's one of my concerns here. The circles I've started with here are not enough. I need to get a little bit larger. Chop the circles up into infinitely small pieces. No. Yeah, sorry about that. Maybe other things is that probably all intersect at the middle, which means the diameter. I don't know, but the diameter needs to be bigger than the radius. I think that's true, and I think it's true of the pink circles I've got right now. So if we put them all going through the middle, difficult question for James. Can I find the middle of this to do like a 5-pointed flower kind of shape? Something I like is that as soon as you start getting close to having them in a nice symmetrical arrangement, the image processing bits of your brain maybe take over and you start to notice that it's lopsided, right? So I just move the circles around, it's not clear what's going on, and then as soon as I put this one here, it's kind of like, that's not good. I don't know, some evolutionary part of my brain. I've become interested in brain science. I only in a very amateur way, but hey. So now as you want to make it perfect, right? Oh, so we've still got one person saying flower of 4 circles, fill in the middle bit. I like it. It's a good idea. It's very symmetric. I sort of want to give it a go. Let's give it a go. So I've got this nice arrangement over here. I might need to make those circles a bit bigger. I'm going to clone this and get some more circles going. This is a different one. I kind of want to make this 4 circle thing, but who is this in chat who's asking for 4 circles? You've asked it a couple of times and I couldn't quite pull it off the last time. Oh yeah, because I didn't know how big to make the bit in the middle. Something like this, I think. So we're not going to do the geometry problem right now for what happens if you do this. Oh, this looks... Oh, the way I've currently done it on the left is a bit silly, because if it's covering a circle, there are these gaps here, right? If this is covering a circle, then it's only going to cover the middle circle. So this is... The way I've currently done it is really bad. Okay, maybe use a 72-degree angle at the middle. Yeah. 72 degrees is 1/5. That's this one, right? This one, you're talking about 72 degrees. You can kind of like... I know what you mean. You want perfect symmetry. Okay, so we've got 2 competing ideas. Not quite this. You want maybe some overlap to make it worth it, so that... You want some amount of overlap. I'm not sure how much overlap you want. So that you can get a slightly bigger circle, like bigger than one of the circles. And these have completely different geometries. So that it's not obvious which one's going to do a better job of covering the blue circle. This one, if we try it out, it's not quite there. Or maybe it's almost there, actually. Oh, not quite. I just can't quite get that bottom bit as well. I think I don't quite have it symmetric enough, or... Oh gosh, I've got some missing bits. I can give up slightly and make the circles a little bit bigger. If I make the circles a little bit bigger, then it's fine. Now it's covering, okay. But the question is, what's the smallest circles I can use? So maybe, we'll go and measure that one later. Maybe this arrangement gives me a better pattern. Oh, it's not doing very well right now. With my current setup, it's not doing very well. I have to make them quite a bit bigger for this to work, right? I have to make the circles quite a bit bigger. And there's all sorts of hard geometry problems here about, given your setup, how big do the circles have to be? I think for this one, maybe I haven't done it very well, but the 4 flower, I had to make the circles quite large for it to actually cover the dot. Whereas my 5 flower, kind of felt like that, covered the dot with slightly smaller circles. Okay, is there a physics stream? Yes, I think it only runs in the autumn and the winter. I don't know if it's running this term. But there's a physics stream by the physics department looking at the physics aptitude test. Okay. Yeah. For the 72-degree ones, can you draw lines to the middle and maybe find the radius? Yeah. Okay, so people are often doing the geometry problem. We don't quite have time to do the geometry problem. The geometry problem is something like the big circle, the blue circle is going to come up to here. So there's this kind of question for what's the relationship between the radius of the pink circles and the radius of the blue circles. It's really nice if you know about the golden ratio. It involves if you know about the golden ratio, the answer involves the golden ratio. There's a hard geometry problem. Well, relatively hard. There are extremely hard geometry problems out there, I suppose. And then for this one, there's a sort of different geometry problem you can do. Surprising fact. Oh, you can think probably the other way round to draw a large circle, try and get them close together. If they're allowed to overlap, then you need to stop me. You probably want to have a rule to stop me putting them all in the same place. I can't actually tell if that's a solution to that problem. How do I want to do this? I think I want to reward everyone first for coming up with great symmetric solutions. The one on the right is especially symmetric. It has, well, no, hang on. The one on the right has got lots of rotational symmetry. The one on the left has got some reflectional symmetry as well. And maybe at home, you're thinking of a different arrangement that's also got some symmetries. Here's the question at the top. How do we know that's the best arrangement? And in some sense, you want to say something like, oh, it's symmetry. I want the most symmetric thing. Like how we were saying before, that it must be 15 degrees because it must be symmetry. It must be in the middle. must be somewhere in the middle. So maybe this 5 thing, it's got to be symmetric and nice. The actual solution is neither of these pictures. There is out there a better way to cover the circles, to cover the blue circles, sorry, using slightly smaller pink circles. The arrangement is a bit odd. It looks like this. Let's look at this image, which is weird, right? So the grey circle here is my blue circle, and these circles that are covering it, this turns out to be the best arrangement of 5 circles to cover one larger grey circle. And it's got, I guess, one reflection symmetry down the middle, but it's neither of the really nice symmetric pictures that we had before. That's a bit of a surprise. If you do it like this, you can use slightly smaller covering pink circles, and it is proven complicated mathematics, not at all obvious, really unusual, that's the best way to do covering a circle with 5 smaller circles. Really hard. It is slightly, it's like the 5 petal thing, but slightly squashed and stretched out. Not obvious at all. And I wanted to show you this as well as the triangle problem, because the triangle problem has this nice sort of symmetry thing, and it's very easy to wave your hands and say, symmetry, it should be nice and symmetric as the answer. Sometimes the answer to a symmetric problem is not symmetric. If you'd like to see more examples of this sort of thing, I've got a page, I don't have a page. There is an amazing page with so many problems. Oh my goodness, I want to show you it now. It's called Eric's Packing Center. The website looks like this. I'm laughing a little bit because Eric has chosen to make the initials of Eric's Packing Center out of packing things together, and also because a packing center sounds a little bit like like the Amazon factory again, right? And Eric has compiled the best known solutions for lots of different problems. Earlier we had triangles inside squares, that's this one, and arrangements of the best way to fit 5 triangles inside a square if you need to send 5 triangles to someone. The best solution, look at that, that's awful. The triangles are wonky. There's quite a famous set of puzzles for putting circles inside squares. Let's see if I can find that one. Circles inside squares? Don't let me down. No. Circles in squares, the second one, there we go. Circles in squares is quite famous. The sort of, you need to send some baked bean tins to somebody. 3 is a little bit like our triangle problem, slightly different, but a little bit like our triangle problem. 4 and 5 make sense. 6 is a bit weird. These are not quite in a hexagonal stacking. 7 is really odd. One of the baked bean tins is rattling around. This is proved in 64. 8 makes sense to me. 9, very nice. Square number makes sense. 10, completely mad. That's the best. Proved in 1990. It's kind of this packing problems contain these nice symmetric solutions, but also some really weird stuff in between. So these packing problems, Eric has got a huge number of different variants of them. Here's if you want to see more circles covering circles. So if you use more than 5 circles, I don't want to spoil it, but sometimes the answer is symmetric, sometimes it's not. Some of these are the best solution we know so far, and some of them are proven to be the best. There are loads of these. I think the packing ones to me feel a bit more like physical problems, because you're trying to put baked bean tins through the post or something. The covering ones are a little bit more funny. There is, and I'll finish on this note, there is a carnival game, a funfair game called Cover the Dot. And it's a carnival game where there's a big red dot on the table, and you have to cover it with 5 metal discs. The discs are a bit smaller, and you have to arrange the 5 metal discs to cover the red spot to win a teddy or something. And this is a carnival game, I think, because the solution's asymmetric. I think if you, the carnival owner, set up the size of the discs just right, I think you can choose it so that the beautiful symmetric arrangement that people might try to do doesn't work, but that it's not rigged, because you can show them the asymmetric layout to show that it's possible. And I think it'd be amazing if that's to prove this theory. I would need to find the carnival running it, and I would need to get them to let me measure their equipment quite precisely, because you only save a little bit by squashing out the pentagon. There are triangles made out of squares. Did somebody say that earlier? Did somebody say fitting squares inside triangles? Yeah, someone said fitting squares inside triangles. Unfortunately, Eric is an amazing mathematician and quite often describes things as trivial. I wish they wouldn't. Trivial is what mathematicians say when something is... It sort of means easy, but often it's a lot of work. So you should not be... If Eric says something is trivial, Eric means it's trivial for Eric. We just spent like half an hour doing this first one. And Eric thinks the next one's trivial, and then the next one was done by Eric, so, you know. Right, okay. I've shown you a link to Eric's packing problems. I should try and get that onto the Maths Club website. There's a link to the Maths Club website on screen at the moment. We're trying to update that with links and other resources and other things you might be interested in. You've ended up now with a carnival trick. Just check Eric's website before you go to the fun fair. Proving these is a lot of work. Looking at all possible configurations is a real science. Right, live and let pi. That sounds like a good tagline to end on. 6 o'clock, so we're going to end the official live stream there. I think we're going to say bye to Prisma. Thank you, Prisma, for moderating. Yeah, quickly, what did I miss on chat? While I was going off on showing Eric's website, people were just saying, wow. Yeah, okay, I didn't miss a lot. Kai wants to know how to prove it. Yep, cool, okay. So I think homework, if you want homework, you don't have to do this, but I like the way that people sent in some Pascal's triangle stuff last week. You might like to go back and look at Pascal's triangle again, and look at these multiples. There was a suggestion in chat that we use multiple colours. From, let's say, multiples of 3, we might use 3 colours instead of 2. Maybe that would look nice. It might have to teach a computer how to display multiple colours. You might like to think about this rows that are all odd problem. And you might like to think about electronics. If there's anyone else out there who wants to code some electronics sealer like Martina did, then I'll be very impressed. You might like to finish off the algebra. I feel like we skipped some steps, or there were some bits I did very fast. So you might like to go back to this triangle problem. And don't try and copy off the screen because it's a mess. But see if you can have another go at working out some triangle stuff. Or you might like to try the geometry of some of these arrangements. And you might like to look into Eric's packing centre for more information about packing things together. Bye everyone. Okay, right. Take care. I will see you again next week in 167 hours for another episode of the Oxford Online Math Club. There is a quick question for Kai in the chat. What program did you use for that? What did you code it with? Was it a program or something else? The triangles give you The triangles give you Venn diagram vibes. These give me Venn diagram vibes as well. Maybe this whole thing was like a big Venn session. Brilliant. Right, Venn diagrams one day. See you in 167 hours for another episode of the Oxford Online Maths Club. Bye. How do I... Nope. This one.